Okay, so let's start. So we have 6.2 today, all about one-to-one functions. Okay. So what does it mean to be a one-to-one function? Well, by definition, a function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. That is, if x1 and x2 are two different inputs of a function, then f is one-to-one if the y value of x1 does not equal the y value of x2. So what this means is that if you are one-to-one, every x has one and only one y value. So every x in the domain has one and only one y value in the range. So the very first blob represents a one-to-one function. So we see that x1 goes to y1, x2 goes to y2, and x3 goes to y3. So this is an example of a one-to-one function. This is what we're going to be focusing on today. The picture to the next picture is a function, but it's not one-to-one. So we see x1 goes to y1 and x2 goes to y1. So here, two x values share the same y value, therefore it is not one-to-one. Again, to be one-to-one, every x must have one y value, one and only one y value. And then the third picture is just not a function at all because one x value has two y values. Okay, so one-to-one, every x has exactly one and only one y value. So here we are given a set of numbers or a set of coordinates, and we want to know, do these represent one-to-one functions? So looking at the first set of coordinates, you have -2, 6, -1, 3, 0, 2, 1, 5, and 2, 8. Do these coordinates represent a one-to-one function? Anybody? Do you see any y values repeated? No. Good. So this set of coordinates would represent a one-to-one function. So we would just say yes. Okay, look at the second set of coordinates, 2, 6, -3, 6, 4, 9, and 1, 10. Does this represent a one-to-one function? So this would be no, because we see that 6 is repeated twice. So we see that two x values share the same y value. Okay. All right. Then graphically, we can determine whether a function is one-to-one by using something called the horizontal line test. So if we are given the graph of a possible one-to-one function, all we have to do is draw a horizontal line through it. And if we intersect the graph once, then it is a one-to-one function. If we intersect it more than once, it is not a one-to-one function. So let's go ahead and look at the graphs below. Here, f of x equals x squared. We know what that looks like. X squared looks like this. And if I were to draw a horizontal line through it, we would intersect it twice. So this means that x squared is not a one-to-one function. Okay, and then look at the graph of x cubed. X cubed looks something like that. If I were to draw a horizontal line anywhere through x cubed, we would only intersect it once. So by the horizontal line test, we see that x cubed is a one-to-one function. Okay, so that's the horizontal line test. Small little theorem here. It says that a function that is increasing on some interval I is a one-to-one function. So what that means is that if you have an all increasing function, then it will be a one-to-one function, such as x cubed. X cubed is an all increasing function. So if it's an all increasing function, or if it's an all decreasing function, then that will be a one-to-one function. Okay, so that's what we're dealing with right now. One-to-one functions. Any questions on this page? What's up, Carl?
Not a whole lot. Eyes hurting me and trying to do homework and be here just in case.
Oh, good. Hope your
Tap me in
exams.
anytime.
Yeah.
Yeah, well, luckily, so I had 3 exams this week. And then the professor made one of them open note, open book, and like have a 4-day due date. And then the other professor was like, I reviewed the syllabus and realized we lost 2 weeks and I didn't account for that. So exams pushed back 2 weeks. So
Nice.
but I'm still catching up on homework I was putting off so I could study.
Yeah. Eek.
Yay, upper division.
Yeah, theory. Don't get behind on that, guys.
Yeah, and don't ever, if you make the mistake of deciding you want to be a math major, never take more than one class in a semester that has the word analysis in the title.
Yep. All right. Okay. So what's fun about one-to-one functions is that if you're one-to-one, you have something called an inverse. So suppose that f is a one-to-one function, then to each x in the domain of f, there is exactly one y in the range. This means that to each y in the range, there is exactly one x in the domain. The correspondence from the range of f back to the domain of f is called the inverse function, and we denote it by this symbol. And no, it's not f to the -1. That symbol says the inverse of f or f inverse. Do not say f to the -1. That is just a notation. So if you see this symbol, this denotes the inverse of a function. Okay, so like we said, if you look at my blobs below, here in the domain, I have an x value, and here in the range, I have a y value. So we said to get from the domain of f to the range of f, so to get from one x value to the one y value, we use function f. And then we said, since it's one-to-one, this means that there is a y value in the range of f that can have an x value in the domain of f. So again, the correspondence to get from y back to x, we use the inverse. So to get from x to y, we use f. To get from y back to x, we use the inverse. And some facts are apparent about that. Well, when you use the inverse function, the range of the original function now becomes the domain of the inverse. And then the domain of the original function becomes the range of the inverse function. So whenever you find an inverse, your domain and range will switch. They'll swap, they'll flip. So whenever you use an inverse, domain and range will switch. Your x and y values will switch as well. All right. And that's all noted here. The domain of the original function becomes the range of the inverse. The range of f becomes the domain of the inverse. Okay. And now, to verify that two functions are inverses of each other, we see that from the above blobs, that if we start with x and use f, and then apply the inverse, we always come back to x. Then if we start from x and apply the inverse, and then apply f, we always come back to x. So no matter what, we will always come back to the value of x. So this means the only way to prove that you have true inverses of each other is to use a method we learned last class, compositions. So we say that if the inverse composes with the original function f of x, and if they are true inverses of each other, they will always cancel and leave you with x. And of course, whenever you compose, you take the domain of the inside function. So here, if you compose f inverse with f, you would take the domain of f. And then another way to do it is to say, if I do f compose with the inverse, and if they are true inverses of each other, it will always cancel to x, where again, you would take the domain of the inside function, the inverse. Okay, so to know that two functions are true inverses of each other, we will compose them. So example 3, verify that these functions are inverses of each other. So to do that, we'll compose them. So we'll compose them the first way. We're going to say g composed with g inverse of x. This means I get g of g inverse of x, which will give me g of the cube root of x, because that's what the g inverse is, or inverse of g is. Now remember, with compositions, we're going to take the cube root of x and plug it into function g for every x. So this will give me the cube root of x to the third. And what is going to happen to the cube root and the cube power? What are they going to do?
Cancel to give you x.
Cancel to give me x. Good. So composing them one way, we arrive at an answer of x, which means that they are definitely inverses of each other. Well, let's go ahead and just prove it going the other way, just to make sure. So 2, we'll do g inverse composed with g of x, and you'll get g inverse of g of x, which will give us g inverse of x cubed, because that's what g of x is. Now, take x cubed and plug it into the inverse function for x. You will get the cube root of x cubed, and again, your powers will what? They'll cancel. Okay, so composing one way and the other, we arrive at x. So what this means is that these functions are true inverses of each other. Okay. Any questions on that one? Okay. So let's try it again. We want to verify that the inverse of f of x is g of x. So we want to prove that the inverse of 2x plus 3 over x plus 4 is 4x minus 3 over 2 minus x. So the only way to prove that those are inverses of each other is, of course, to compose them with each other. So let's go ahead and do that. Gonna need more room. How's that? Okay. So we'll say 1 would do f compose g of x. This will give me f of g of x, which function g is 4x minus 3 over 2 minus x. So we're going to take all of function g and plug it into function f for every x. Ooh, lots of algebra, right? So we're going to get 2 times 4x minus 3 over 2 minus x plus 3 over 4x minus 3 over 2 minus x plus 4. Okay, we have just plugged it into function f. Now let's go ahead and simplify. And we're going to need to clean up the numerator and the denominator. So we're going to need to put these two terms together, meaning we need a common denominator. So what we're going to do is put 3 over 1 and multiply by what common denominator?
2 minus x.
2 minus x. And we'll do the same below. You'll put 4 over 1 and multiply by 2 minus x. Okay, here's what we're going to have. 2 times 4x minus 3 plus 3 times 2 minus x over the same denominator of 2 minus x. This is everything that's in the numerator. Since we got a common denominator, we can put the numerators together. And this is all over 4x minus 3 plus 4 times 2 minus x over 2 minus x. So we've just got common denominators. We put the numerators together, the numerator in the numerator and the numerator in the denominator. We put those together. And now we just have to simplify. So distribute that to 8x minus 6 plus 6 minus 3x over the same 2 minus x. And then down here, 4x minus 3 plus 8 minus 4x over the same denominator of 2 minus x. Okay, clean up again. And you'll get 5x over 2 minus x over, what's that? That's going to be 5 over 2 minus x. Okay, so we're almost there. You have fraction over a fraction. So now we multiply by the reciprocal. 5x over 2 minus x times 2 minus x over 5. And what's going to cancel?
the 2 minus x,
And what else?
and the 5s,
And what are we left with?
x.
So does this prove that they are inverses of each other?
Yes.
Unfortunately, right? Do we want to see the proof going the other way, or do we trust this one?
What's the harm in more algebra?
I was leaving it up to them. Since they don't say anything, I guess we should do it, huh?
Will there be scenarios where we would have to prove it the other way around?
I don't think so.
Then I would say trust it.
If you want to be for the purposes of this class, no, but if you want to actually be right, you haven't proved anything until you prove it the other direction, because it's an if and only if.
That is true. Oh, man. Well, then. Yeah, we got time, right? Why not? Way to go, Carl.
You're welcome.
Algebra all day. You get G of 2x plus 3 over x plus 4. Why not? Bam. And this becomes, so you take F, you plug it into G, and we're going to have 4 times 2x plus 3 over, not that, over x plus 4 minus 3 over 2 minus 2x plus 3 2x plus 3 over x plus 4. Beautiful. And same thing here. Put 3 over 1. Get your common denominator of x plus 4. Same thing down here. 2 over 1. Common denominator of x plus 4. And then put your numerators together. 4 times 2x plus 3 minus 3 times x plus 4 over x plus 4 over 2 times x plus 4 minus 2x plus 3 over that same denominator. There we go. And clean up. 8x plus 12 minus 3x minus 12 over x plus 4 over 2x plus 8 minus 2x minus 3 over x plus 4. And we get 5x over x plus 4 over 5 over x plus 4. And once again, reciprocate. And look what we have. Cancel, 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 cancel. And this has definitely proven that F and G are true inverses of each other. All the fraction math you can handle. All right. Any questions on checking or verifying inverses?
Sounds kind of goofy.
Sounds goofy. All right. Next is about the graph of inverse functions. So the graph of a one-to-one function and its inverse are going to be symmetric with the line y equals x. So if you have the one-to-one function and its inverse, and you graph them, you will see that they reflect or are symmetric across this line, y equals x. So point A here reflects over here and gives you its complement. And then point B here reflects over and you get the reflected point of B. Okay, so graphically, to tell that they're inverses, they're symmetric about the line y equals x. Okay, now let's go ahead and try it. So we're given points and we want to plot them, see if it's one-to-one. And if this graph is one-to-one, then it'll definitely have an inverse. And we will reflect it across that line y equals x. All right. So let me expand my graph a bit. Let's just say that this is 0, that's 1, that's 2, there's -1, there's -2, just using the space up. And then make that a 1 and make that -1. Okay, go ahead and plot the first points. -2, -1. It's going to be right there. We can make that bigger. There we go. And then -1, 0. And then 2 and 1. So here's what our first function looks like. Probably a little more straight. There we go. Okay, so this is definitely one-to-one because if I draw a horizontal line through it, I intersect it only once, which means it's going to have an inverse. Okay, so the line y equals x, to draw that, well, it's basically 1 for 1. If x is 1, y is 1. If x is 2, y is 2, so on and so forth. So let me just draw that line real fast. 0, 0, 1, 1, 2, 2. So it would look something like this. I'm just going to make it dashed. Okay, so now let's plot the other function, the inverse. And all we're going to do, so since it's a one-to-one function and it has an inverse, your x and y values will swap. They'll flip over. So let me write that over here. I'll say the inverse. This means -2, 1 becomes -1, -2. And then -1, 0 becomes 0, -1. And 2, 1 becomes 1, 2. So I need to go up to 2 now. So that'll be -2 and that'll be 2. Okay. So -1, -2 right there. And then 0, -1, and then 1, 2. There we go. Now, my graph may not look like it, but yours may. Do these look symmetric across the line y equals x?
Yes.
Good. My points are reflected here. This is 0, -1. If I reflect it over, I get -1, 0. There we go. Not bad. So that's graphically. So if you have an inverse, your one-to-one function and your inverse will reflect across this line. Okay. Any questions on that page? All right. Now let's get into the math of finding in inverse. So the fact that the graphs of a one-to-one function and its inverse are symmetric with respect to the line y equals x, we can find the inverse by interchanging the roles of x and y. So here are a couple steps to finding the inverse, but I'll walk through them with you while we go through the steps. So let's start with this example and we'll go through the steps with them. So find the inverse of x cubed minus 1, and then graph both functions on the same axes, so on the same coordinate plane. Okay, so our steps for finding the inverse. All right, here's going to be step 1. Here, I'll call this find the inverse. Okay, so step 1 in finding the inverse. You're going to change the equation to y equals x cubed minus 1. So that's step 1. Step 2, you are going to interchange the roles of x and y. Since x cubed minus 1 is a one-to-one function, well, we're assuming it's a one-to-one function because they gave it to us. Since it's a one-to-one function, it's going to have an inverse, which means your domain and range switch places and your x and y values switch places. So on step 2, we interchange their roles. So this means that I now write the equation as x equals y cubed minus 1. So we interchange the roles of x and y. And then step 3, we solve for y. Okay, so step 3, solve for y. So using the equation above, add that 1 over, you get x plus 1 equal to y cubed. And then to get y all by itself, what would you do to both sides?
Cube it.
It's already cubed, so to
So
get
take
rid of
the
the cube, you would
Cube root.
cube root it. There you go.
Yeah.
So we'd say the cube root of x plus 1 equal to the cube root of y cubed. And we would end up with the cube root of x plus 1 equal to y. Okay, and then step 4, state it as the inverse. So we're going to say f inverse of x is equal to the cube root of x plus 1. There it is. There's our inverse. And now we want to graph both functions. So what we're going to do is graph the original function x cubed minus 1. So let me make an XY chart for that. So here we have x and y equals x cubed minus 1. And the most common points to pick when graphing a function is -2, -1, 0, 1, 2. And these are going to be the only actual values that fit on the graph below, unless we made the intervals appropriate. But if you ever need to know how to graph a function, pick points. And the most common points to pick are -2 to 2. Okay, now plug all of these x values in to this function. And you'll get -2 cubed, which is -8 minus 1. You'll get -9. If you plug in -1, you'll get -1 cubed, which is -1. Minus 1 gives me -2. Plug in 0, you get -1, plug in 1, you get 0, and then plug in 2, you'll get 7. Okay, so let's go ahead and plot the original function. I will leave the x and y values as is. So -2, -9 is right here. -1, -2, 0, -1, 1, 0, and then 2, 7. 1, 2, 3, 4, 6, 7. There we go. Okay, and let me connect. Here's f of x. Okay. And now let's go ahead and graph the inverse. Do I need to pick new points?
No, because you could take the inverse of the points that you already created.
Good. So whenever you graph the original function, and if it has an inverse, all you're going to do is take these coordinates and flip them. So you'll get -9, -2, -2, -1, -1, 0, 0, 1, and 7, 2. Okay. Easy enough, right? Take those original coordinates and flip them. Now let's plot this function. -9, -2, right there. -2, -1, -1, 0, 0, 1, and 7, 2. 1, 2, 3, 2. And connect. No. And there's our inverse. Okay. And now, if these are true inverses of each other, then they are going to be symmetric about the line y equals x. Do these graphs look symmetric across this line?
Yes.
Yeah. So if this point is 7, 2, and I reflect it over here, what is this point?
2, 7.
2, 7. That's it. Same with all the other ones, right?
Looks like.
Okay. Oh, yeah. And in this case, if we want a domain and range, I might as well just write it down for an example. Let's look at x cubed minus 1. X cubed minus 1 is a polynomial. What is the domain of all polynomials?
All real numbers.
All real numbers. And then what is the range of this function? Of the original function?
All real numbers.
All real numbers. Good. Because your tails go to negative
Yeah.
infinity and positive infinity. Okay. Which means that if you have the domain and range of the original function, then you know if your x and y values switch, your domain and range will also switch. But this one's just way too easy because the domain and range are exactly the same. So this means that for the domain of our inverse, it would be all real numbers. And the range of our inverse would be all real numbers. But let's say that we had something different. Let's say domain was 0 to infinity and range was, let's say, like -1 to 5. And then you found the inverse. What would my domain be now?
Negative infinity to 0.
No. So you take these and you just
Oh, -1 to 5.
-1 to 5. And what would my range be?
0 to infinity.
That's it. So whatever your domain and range are for the original, you would flip them, switch them, swap them for the inverse. And the same could be said for the inverse. Let's say you had the inverse's domain and range. Then you would swap those to get the original function's domain and range. This example was just too easy because their domain and ranges are exactly the same, all real numbers. Okay. And yes, you can also check algebraically by composing them to see if they're the inverse. But since we graphed it and they are symmetric about that line y equals x, this definitely proves that they are inverses of each other. Okay. Any questions on that page? Want one, Carl?
Hell yeah.
All right. I need to send you the link.
Please.
Copy and send to Carl. Boom. Cool. All right.
My eyes.
So you got finding the inverse.
That's all you want me to do is find the inverse? You want me to do domain and range?
Oh yeah. Sorry. You'll do the whole thing.
Get this thing opened up here.
Yeah, so it's find the inverse, then the domain and range for F and the inverse. And then it says check the result. Oh boy.
Gotcha. Is this is 6-2, right? Yeah.
Yeah, 6-2. Look for the 2021.
2021. Yeah, I got it. Okay, let me share my screen. Okay.
Woohoo.
Did I go too far? I think I went too far. Okay, there we go. All right. It's a little big. A little bit smaller. 0.7, just like I left my pencils. Okay, so we want to find the inverse of this f and do our domain and range. Okay, so the way I like to do them is the way Robert taught me a long time ago, so I have to imagine it's going to be pretty similar. So I start with this. F of x equals 2x plus 1, x minus 1, y equals 2x plus 1, x minus 1, and swap all your variables. And then you want to solve back for y. So we're going to start by multiplying this here up to here, right? So we'll have x times y minus 1 equals 2y plus 1. Distribute this x. Xy minus x equals 2y plus 1. And then the next thing we're going to want to do is to collect terms. And we'll have xy minus 2y will equal x plus 1. We added an x to both sides, subtracted a 2y from both sides. We're going to factor out this y, x minus 2, x plus 1, and then just divide. Oops, wrote that a little goop. What just happened to my computer? There we go. Okay, make sure that's working right. There we go. Y will equal x plus 1 divided by x minus 2. And then, of course, we want to write back in for this y our f inverse of x equals x plus 1, x minus 2. Cool. The next thing to consider, let me minimize that a little bit. So we want to find our domain and range. Let me get a different color. Let's do it in purple. Right, so the domain of f, the range of f, and then we want the domain of f inverse and the range of f inverse. Now, usually what I do is I just try to find the domain of f first and then find the domain of f inverse. And that gives me the range of both of them, and I don't have to think any harder about it, right? Because these two just swap around, right? This one is this one, and this one is this one. So if I just find the domain, usually finding the domain is easier, right? So if I just find the domain of both of them, then we're good. So I'll do that as side work down here. Let's do orange. Why not? Make this colorful. So my domain of f of x, right? That's going to be what we got. We got for 2x plus 1, x minus 1. We only need to consider the denominator, right? So we'll do x minus 1 cannot equal 0, because that's the only thing that could potentially give us an undefined solution or a non-real solution here. So we'll get that x cannot equal 1. And then I'll do the same thing with the f inverse, right? So that will give me got x plus 1 over x minus 2. Same deal. We only want to look at this for our denominator. Say x minus 2 can't equal 0. X cannot equal 2, right? So come back up here real quick. So my domain of f is x cannot equal 1. Or you could write this as negative infinity to 1 union 1 to infinity. Our domain of f inverse is x cannot equal 2, which is negative infinity to 2 union 2 to infinity. And then this part here is also our range of f, negative infinity to 2 union 2 to infinity. And our domain of f is the range of f inverse, negative infinity to 1 union 1 to infinity. And you're done. Any questions on that? I went a little fast.
Check that they're inverses.
Oh yeah, we have to check that they're inverses. Whoops, I forgot that part. Okay, so let me go ahead and do that. Check that they're inverses real quick. Oh, let's do sky blue. Okay, so to check that they're inverses, you can do it one of two ways. You can either do f composed of f inverse of x, but this should equal theoretically f inverse of x composed of f of x if they are inverses, right? So I'll just check this one. So let's do, what were my original functions? It was 2x plus 1? Yeah. So we're going to have, that'll be 2 times x plus 1 over x minus 2 plus 1 divided by, and then it was x minus 1, right? Yep. X plus 1, x minus 2, plus minus 1. Cool. So then this will be equal to 2x plus 2. You just multiply the 2 to the numerator divided by x minus 2. We're going to turn this plus 1 into a fraction of x minus 2. So it'll be plus x minus 2 over x minus 2. Divide this entire thing by x plus 1 over x minus 2 minus x minus 2 over x minus 2, right? And then this will be equal to, we're just going to combine the numerators. So we get 2x plus x is 3x. 2 minus 2 is 0. X minus 2 divided by x minus x is 0, right? And this is going to be 1 minus negative 1 is a 2. This is a 3, right? So 1 minus plus 1 plus 2 is 3 over x minus 2. So to resolve this, there's two ways you could do it. I'll show you both. The simple, or sort of like the non-thinking way, I guess, is to put it, is to just do the division as we would normally see it. Divide 3 x minus 2. So that, of course, becomes 3x over x minus 2 times x minus 2 over 3. This 3 cancels to 1. This entire 1 cancels to 1. We're left with x over 1 times 1 over 1, which is just x. The other way to do it is to notice, let me do this in, that won't be seeable. Let's do brown, why not? You know what? Nah, we haven't done any black. Let's do some black. So the other thing to notice, right, is that you have a fraction here with one number in a numerator and the same number in the numerator of the fraction it's being divided by. So you can just cancel those right out. And then this whole thing right here that's in the denominator is the same as the denominator of this fraction. So this whole thing just cancels out. So what you're left with is just x over 1 over 1 over 1. These ones just go away because you're dividing by 1 the whole way down, and you get x. And there you go. So it works out. And that is that. Any questions on any of that? That was a lot of stuff really quick. So
Everybody
all
good
right.
with that?
I will take the silence as I did a good job. Either that or I left everyone more confused than when we started, in which case I'm sorry.
Is anyone out there?
Right? I gotta go get a box of crayons for my Marines.
Hey now.
All right.
I
Cool.
actually think I do have like a whole bunch of boxes of crayons in the other room.
Okay. So this page is actually pretty cool because we talk about restricting certain functions' domains. So the reason why we want to do this is so we can make any function a one-to-one function. So we saw earlier on the very first page that x squared was not a one-to-one function, because if I drew a horizontal line through it, it would intersect it twice. Well, here's where you have the power of math. You can take any function and restrict its domain to become a one-to-one function. So this is a very important concept when you guys get to pre-cal and start learning inverse trig functions. Trigonometric functions are not one-to-one. but you can restrict their domains to make them one-to-one. And if you make any function a one-to-one function, then you can definitely find its inverse. Okay, so for this problem, we're given x squared plus 1, but now the domain has been restricted to any x value greater than or equal to 0. So let's go ahead and graph f of x first, just to make sure it is a one-to-one function. So x squared plus 1. All right. So I'll put that info over here on this side. So here's f of x equals x squared plus 1. The domain we just saw is any number greater, any x value greater than or equal to 0. The range, well, we'll figure that out in a second. Let's go ahead and graph this. So I'll make my XY chart here. And the domain's already telling us what x values to pick. It says choose anything greater than or equal to 0. So this means we're going to start at 0 and just go greater than. 1, 2, 3. I don't think anything bigger than 3 will fit on our graph. Well, the y value wouldn't. So take all these x values and plug them into this function, x squared plus 1. 0 squared plus 1 is 1. 1 squared plus 1 is 2. 2 squared plus 1 gives me 5. And 3 squared plus 1 gives me 10. So I think I only need this part of the graph. So if I'm to plot the first function, you have 0, 1, 1, 2, 2, 5, and 3, 10. So here is x squared plus 1, a domain restricted x squared plus 1. And now, if I draw a horizontal line through it, I only intersect it once, which means this is definitely a one-to-one function now, which means we can find its inverse. So let's go ahead and do that. Oh, I guess before we do that, let's look at the range. What is the range of this function? What y value do we start at?
1
1.
to infinity.
Good. So 1 to infinity. Or we could even say y greater than or equal to 1. Okay, that's figured out. Now let's go ahead and find this inverse. Step 1, have it as y equals x squared plus 1. Step 2, interchange. Make it x equals y squared plus 1. So we interchange the roles. Step 3, solve. So subtract that 1 over. You get x minus 1 equals y squared. And what are you going to do to both sides?
Square it. Or, sorry, cube root.
Well,
Sorry. Never mind.
square root. You got it. So here you get plus or minus the square root of x minus 1 equal to y. All right. But which one do we keep? Do we keep the positive square root or the negative square root?
The negative.
And this will all depend on our domain. Look at the domain of the original function. If you're greater than or equal to 0, and if you're greater than or equal to 1, does that mean you have all positive or all negative numbers?
All positive.
So we only keep the positive one. So step 4, we have the inverse as the square root, positive square root of x minus 1. There we go. Now let's graph it. So I'll put this here. F inverse of x equals the square root of x minus 1. Here's domain. Here's range. What is the domain of this function?
Zero to infinity.
Remember when you have an inverse, your domain and range.
Oh, right.
I'm seeing an imaginary domain. Or I'm getting an imaginary. Sorry.
Just
Oh, 1 to infinity.
switch those around. There you go. 1 to infinity. And what's your range?
Oh, x is greater than or equal to 0.
Well, remember when you go to range, it becomes y
0 to
value,
infinity.
right? Good. So this would be or 0 to infinity. So this means you'd have 0 to infinity. Okay. And now for your XY chart, again, do we need to pick new points? Anybody? Anybody? Do I need to pick new values? Or do I take this table and flip it?
Take the same table.
Good. And flip the XY values. And graph it. 1, 0 here. 2, 1. 2, 4, 5, 2, and 10, 3. And there is my inverse. And do these graphs look symmetric about this line, y equals x?
Yes.
Yes. Good. Here's the point 5, 2. Reflect it over 2, 5. Okay. And there you go, guys. Those are one-to-one functions and inverses.